2-kilogram block. It's released from rest at the top of a frictionless incline. The incline makes an angle of 30 degrees with the horizontal. After traveling 1.5 meters down the incline, the box hits and compresses a spring with spring constant 120 newtons per meter. How far does the box compress the spring? So let's do a little sketch. Here's our box. So there's a spring down here. The spring is initially not stretched or compressed. It's not connected to the box at all. It's just sitting there. This distance between the box and the spring is the 1.5 meters. But when the box hits the spring, it's going to cause the spring to compress. Some distance. That's what we're looking for. It's how far the spring gets compressed. Now, granted, the box isn't just going to compress the spring and stay there. The spring will push it back up the incline. But we're not worried about that. We're just worried with the compression of the spring so that we can find how far the spring gets compressed. Now, our equation, our conservation of energy equation, is still perfectly valid. We derived the equation for free fall alone, so only gravity causing the object to accelerate. We derived the equation for springs. Turns out the equation works for springs and gravity together. So we can still say the initial potential energy plus the initial kinetic energy has to equal the final potential energy plus the final kinetic energy. The only way this is not going to be true is if our incline was friction, or frictionful. If it had friction. How to say that grammatically correct. Gratefully, we have a frictionless incline, so we don't have to worry about that. The other way it wouldn't work is if drag was significant. I'm going to assume drag is not significant in this case. So this is perfectly valid. But we have to think in our minds and remember that potential energy can be gravitational potential energy, and it could be both. Elastic potential energy and gravitational, or it could be one or the other. So we have to think about both types of potential energy when we look at a problem. So let's approach it the same way. Let's go ahead and choose our location where we want y to be 0. Where would you like to make y equal 0? Do you know what? I'm going to just veto everybody. I'm going to put it at the bottom. Someone else agreed with that. It's just a special thing of mine. I like to make my lowest point 0. You don't have to. But since I'm the one right down on the board, I'm going to choose to. Okay. So that means at this lowest point, the gravitational potential energy will be 0. Gravitational potential energy depends upon where you choose y to be 0. It's really arbitrary. It doesn't really matter because the equation only depends upon the change in potential energy. So wherever you call y equals 0, it doesn't matter because the change overall will still be the same. What about the elastic potential energy of the spring? At this very lowest point, will the spring be storing any energy? Yes. The spring is compressed. It's compressed by a distance we're calling x. So our equation is 1/2 k x squared. Remember, in our equation for potential energy for a spring, elastic potential energy, you cannot choose x to be 0 wherever you want. It's not arbitrary. Remember, we derived this equation with the understanding that x equals 0 is when the spring was not compressed or stretched. X can only be 0 if the spring is not stretched or compressed. Down here at the lowest point, we know the spring has become compressed. Therefore, it has potential energy. It's compressed by a distance of x. While we're at it, let's talk about the kinetic energy down here. Will the box, at the instant it has completely compressed the spring as far as it possibly can, will the box be moving? No. So it will have no kinetic energy. Okay. Initially, up here, because we're not at y equals 0, there will be gravitational potential energies. So there will be an mgy initial. What about the spring? When the mass is sitting at the top of the incline, will the spring be storing any energy? No. So the elastic potential energy is 0. What about the kinetic energy? It's also 0. It was released from rest. If its speed is 0 at that instant, it can't have any kinetic energy at that instant. So all of this energy we're starting with, the mgy initial, has to equal all of the energy we're ending with. 1/2 kx squared. Now energy is really nice to relate initial to final points, but it does not tell you anything about what happened in between. Just because the kinetic energy was 0 initially and finally here, doesn't mean it never had any kinetic energy. As the box starts sliding down the incline, this gravitational potential energy decreases. As the potential energy decreases, the kinetic energy increases. Keep sliding down, kinetic energy increases until it hits the spring. Now it starts to compress the spring. The kinetic energy decreases and the elastic potential energy increases. So energy, really nice to relate initial and final points, not so useful for telling us what happens in between. Okay? If you want to figure out what happens in between, you have to make that point one of your initial or final. Okay, let's go ahead and figure out what y initial is.
1.5 sine 30.
That would be from there. We need to measure from the bottom. (1.5 times x, or sorry, plus x times the sine of 30. Are you okay with that? So total distance is 1.5 plus some extra distance x. So the total distance down the incline is 1.5 plus x. To get the vertical component, we have to multiply by the sine of 30. Okay, so let's factor this out. We're going to get mg times 1.5 sine of 30 plus mgx sine of 30. I'm going to bring this to the other side because I'm noticing right now that we have x squared, x, and no x term. I'm going to have to do the quadratic equation. So we know the mass. Mass is 2 kilograms, g is 9.8. So this term's 14.7. x minus 1/2, k is 120, so minus 60x squared is equal to 0. So quadratic equation is required. I'm going to let my calculator do it for me, since it will. I get a negative answer of 0.42 and a positive answer of 0.58. Which do you think is the correct answer? Positive.
What happened to the sine 30 on the 9?
Well, 2 times 9.8 times the sine of 30. Sine of 30 is 1/2.
Okay.
The 2 and the 1/2 cancel, leaving us with the 9.8. So our spring is compressed by 58 centimeters. That's how far it gets compressed. Nice thing is, we wouldn't have been able to use kinematic equations to do this problem, because springs do not apply constant forces. The acceleration of the block from the top to the absolute bottom was not constant. So kinematic equations would not work. But energy, it doesn't care if acceleration was constant or not. We've already derived the equation for the potential energy. Yes?
Is the strength of the spring the 120 spring?
Yeah, so the 120 newtons over meter is related to the strength of the spring.
Where was that?
That's why I got 60 right there. Because 1/2 of 120 was 60. So yes, that was important. How strong the spring is very important. Now, of course, I'm assuming the spring was capable of compressing this far as well.